Hello, my name is Adrian, and today I'll be talking about unitary property testing lower bounds by polynomials. This is joint work with my advisor Henry from Columbia University, and I will introduce what the unitary property testing problem is, and then followed this by the two main contributions in our paper, which are the generalized polynomial method and an application of this method to property testing with quantum proofs. So the quantum query complexity is central in the study of quantum computing. And in this model, an algorithm queries a bits of a Boolean string in superposition in order to compute some function or property of this string x. And in general, one wants to come up with an algorithm that minimizes the number of queries made to the string x. So why study quantum query complexity? Firstly, it captures many of the known quantum algorithms, such as Grover's search and the quantum period finding algorithm, which is the basis for the quantum speedup in Shor's factoring algorithm. Secondly, since we can actually prove lower bounds for query complexity, unlike in many other models of computational complexity, this enables a rigorous comparison between classical algorithms and quantum algorithms for solving a particular problem. Finally, when we able to prove lower bounds on quantum query complexity, this provides insight onto the maximum possible quantum advantage that's possible for a particular problem. And for the rest of this talk, we'll be focusing on lower bounds. There have been two main paradigms for proving lower bounds of quantum query complexity, namely the adversary method and the polynomial method. And we'll be focusing on the polynomial method in this talk. The polynomial method was introduced in a paper by Beals and others in 2001, and which states the following observation, that given the P, which is the acceptance probability of a T-query quantum algorithm on a particular input X, then a P can be expressed as a polynomial of degree at most 2T, which is not too much greater than the original query complexity. Hence, this implies that if the algorithm computes some function f with a bounded error, then this polynomial is a good approximation to the function f, and furthermore, it has degree at most 2t. Therefore, showing that there's no low-degree polynomial approximation for a particular function f implies that there is no quantum query algorithm that uses a small number of queries for computing that. And this powerful observation has been used many times in the quantum query complexity literature. However, while this method has been very useful, the inputs and outputs are still classical strings. And not all realms of interest in quantum complexity theory can be analyzed in this way. And this is because, in general, an experimenter could be interested in studying an arbitrary quantum system, which is modeled by a unitary operator U. This being a matrix is quite different from a classical string. However, the standard query model is indeed a special case for defining the query to a string as a unitary that maps the basis state I to plus or minus I, depending on the ith bit of the string. So what are some examples of these unitary property testing problems that aren't captured by the standard string model? Some of these problems might actually have a reasonable classical analog. For instance, in the dimension counting problem, one is given access to a unitary of the form I minus 2p, where p is projector onto a subspace. And one wants to check if this subspace has some dimension less than or equal to W, or dimension at least 2W for some parameter W. This is can be argued to be analogous to the problem of approximately counting the Hamming weight of a string, which has been studied in the quantum query complexity literature. And indeed, we're able to leverage these lower bounds in order to prove a lower bound on a dimension counting problem. However, we also have other problems that do not appear to reduce to a natural classical analog. The first such example of a problem that we study is the unitary recurrence time problem, which is to determine if, given a unitary U, whether or not after T applications it becomes the identity, or if d to the T is epsilon far away from the identity matrix. Such problems arise in the study of quantum dynamics and quantum chaos. Another example is testing entanglement properties, which is promised that U is a reflection about some quantum state in CD tensor CT. We would like to find some way to estimate the entanglement entropy of that state. Again, entanglement properties and entanglement entropy are very natural to study in the context of quantum physics and chemistry. Finally, we have the example of testing Hamiltonian properties, which is promised that U is the time evolution operator associated to some Hamiltonian H. We would like to check properties of this Hamiltonian H, which one such example would be to test if it's geometrically local or not. And such problems can naturally arise in the context of quantum experiments in physics. So it seems as though we require new techniques to analyze the complexity of these inherently quantum problems. And we argue that the generalized polynomial method is one such way to analyze these problems. From the perspective of computer science and complexity theory, unitary property testing problems are also interesting, since there is a connection between query lower bound and oracle separations of complexity classes. For instance, the Grover search lower bound leads to an oracle separation between the complexity classes BQP and NP. And query lower bounds on unitary property testing problems similarly lead to oracle separations between quantum complexity classes. This idea was already used by Ernst and Kuperberg to give an oracle separation between the classes QCMA and QMA. And we propose an approach using unitary property testing for an oracle separation between QMA and QMA2. We'll revisit this towards the end of the talk. So now that we've given some examples of unitary property testing problems and argued why they're interesting to study, we now state our generalized polynomial method that we use to analyze these questions. So we firstly show that if we have a T-query quantum algorithm that's able to query some unknown unitary U and its inverse, then the acceptance probability can be expressed as a degree 2T polynomial in the matrix entries of this unknown unitary U. And furthermore, this polynomial has some nice properties, such as it is a self-adjoint polynomial. However, this observation alone is not very useful for lower bounds. This polynomial that we get is a multivariable polynomial, and in general, it is very hard to prove lower bounds on such polynomials. Usually, the lower bound techniques for degree work best when there's a small number of variables. However, we can observe that we can exploit the symmetries of a unitary property testing problem to reduce the number of variables and thereby prove lower bounds. We show how we do this for the recurrence time problem that we introduced. So we observe that this property is actually a unitarily invariant property. That is, if a unitary U satisfies the yes condition or the no condition of the problem, so does VU V conjugate for any unitary V. In particular, this shows that whether or not U satisfies the property depends only on the eigenvalues of U. So we exploit this symmetry to show that the acceptance probability for any t-query algorithm for the recurrence type problem is not only a polynomial in the matrix entries of U. In fact, it is a very special kind of polynomial. In fact, it can be written as a degree at most 2t polynomial in the eigenvalues of U that is also a symmetric polynomial. And more generally, this applies for any unitarily invariant property. So this observation is quite interesting because we've reduced the number of variables from order d squared to order d. And furthermore, we've reduced the number of possibilities for the polynomial p that describes the acceptance probability. We get that it's not just any polynomial, it's in fact a symmetric polynomial. So by further reducing this polynomial to a two-variable polynomial, we're able to obtain the following lower bound for the recurrence type problem, that any algorithm must use at least t over epsilon of queries or a square root of d queries. And we compare this to the upper bound we get of t times root d, which uses the quantum amplitude amplification algorithm. We also apply our techniques to the entanglement entropy problem, which we recall is to decide whether or not a given state has entanglement entropy at most A or at least 2A for some parameter A. While this problem does not have a full unitary symmetry, it has some symmetry, which is a local unitary symmetry. That is, a given state has a high entanglement entropy if and only if some tensor product unitary U tensor V applied to the state also has high entanglement entropy. We exploit this local unitary symmetry to show that the acceptance probability of a t-query algorithm for the entanglement entropy problem can be written as a symmetric polynomial in the eigenvalues of rho, which is the reduced density matrix of the state psi. Using this theorem, we're able to show the following lower bound, that any quantum algorithm for the entanglement entropy problem must use exponential of 8 divided by 4 queries. In particular, we also show a general connection between the symmetries of a property testing problem and the properties of a polynomial that encodes the acceptance probability for any tester for this property P. This relies on the concepts of invariant rings that is studied in abstract algebra, and we leave the details of this to our paper. Finally, we describe an application to property testing with quantum proofs. In this model, the tester receives access to the unitary view and a quantum state that supposedly certifies that U is a yes instance. We call this the QMA property testing model in analogy to the QMA complexity class of problems that can be verified efficiently by a polynomial-sized quantum circuit with access to a polynomial-sized proof state. This model motivates the question of when quantum proofs provide speedups or when they are useless. One advantage of the polynomial method is that the polynomial method enables us to immediately prove lower bounds on the property testing problems that we study in the QMA setting. And we state our lower bounds here for the recurrence time problem and the entanglement entropy problem on the slide. These are quite similar to the BQP lower bounds, except with the additional parameter M, which is the number of qubits in the witness. However, QMA is also interesting as the definition can be modified to study the power of different types of quantum proofs. One such setting is the QMA2 setting, where the verifier has access to two unentangled proofs. That is, a proof state of the form psi1 tensor psi2, where each of psi1 and psi2 are polynomially sized. We note that QMA is always contained in QMA2, as a verifier can always ignore one of the proofs and act as a QMA verifier. However, an oracle separation between QMA and QMA2 has been a long-standing problem in quantum complexity theory. In particular, an oracle separation would resolve Watrous' disentangler conjecture. And furthermore, the only complexity classes that are known presently are that QMA2 is contained in NX, and this appears to be a vast complexity gap. QMA2 also has some very interesting properties, such as there's a theorem by Aronson et al. That states that there's a QMA2 protocol for FreeSat on n variables, where each proof state contains square root of n qubits. This appears to be quite counterintuitive, as it seems as though a linear number of qubits would be necessary. And indeed, this is not believed to be true for QMA, assuming the exponential time hypothesis. Our last contribution in this paper is to describe a possible approach for the QMA versus QMA2 problem. We introduced the entangled subspace problem, which is given oracle access to a unitary that encodes some subspace S of CD tensor CD to check whether or not there's a state in S that is either close to a product state, or if all states in S are far away from being product. We show that this can be tested by a QMA2 verifier and conjecture that cannot be tested by a QMA verifier. In particular, towards this conjecture, we show a lower bound against QCMA, which is the subclass of QMA that has a quantum verifier, but a classical witness. And additionally, we present other observations about the entangled subspace problem, such as some observations about average case versions of this problem, where P is chosen randomly. The main open problem left by this work is to prove a strong QMA lower bound for the entangled subspace problem. We observed that the problem has a local unitary symmetry, and so we expect our observations that connect symmetries of property testing problems to lower bounds to be useful in this setting. Secondly, We do not have tight lower bounds for some of our problems, such as the recurrence time problem introduced earlier. And plus, it's interesting to prove, to see if our techniques can be extended to prove tight lower bounds for this problem in the BQP and QMA settings. Finally, as all of the problems that we discuss have unitary or local unitary symmetries, it would be interesting to investigate whether or not our methods can be used for problems with other types of symmetries. Thank you for your time.